The problem is that it remains that previously we have assumed it was an ideal op-amp where the open loop gain was equal to infinity, but in reality open loop gain is more like 10 to the third or 10 to the fourth or 10 to the fifth. It is still a big number, but it is not infinity. So if it's not infinity, then we're saying that the open loop gain in reality is finite, like finite here. So therefore there will be a limitation on the closed loop gain, so this results in a limitation to closed loop gain from the compared to the ideal. Okay, so what happens to this gain equations, input-output relationships, if a is not infinity? Yeah, so we just repeat the circuit solving. So I'm just redrawing the circuit, and then we have the input and output. So I'm just redrawing the circuit, and okay, so let's go back to the fundamentals of what is the op-amp it does. So from day one we said that V out is equal to, for just the op-amp basic equations, is equal to the open loop gain multiplied by V in D, which is actually is V plus minus V minus. Now for this circuit, because V plus is V in, so then we say, well, then V out is equal to A times V in minus V minus. So this is like the fundamentals that we learned from day one, and I'm going to solve for V minus now. So I will say, okay, V out divided by A is equal to V in minus V minus, and so then solve for V minus is equal to V in minus V out divided by A. Okay, so like before, we're going to assume that no current goes into the inputs for the op-amp, and so that the only current is going through here is called I1. We call that I1, and the I1 path is going here, and there's no current going here. That's 0, and this is also 0. Yeah, so let's define this current path. The same thing we did before, but we're just going to write it again. So I1 is equal to, as defined by, is this voltage minus this voltage divided by this resistor. So it is 0 minus V minus divided by R1. Another way of writing I1 says that is this voltage minus this voltage divided by this resistor. So it is V minus minus V out divided by R2. So this is just our KCL. I guess KCL and KVL, but okay, just KCL. So the thing is, like, we need to substitute this like v minus equation that we have found, and we need to substitute this into these parts, into this v minus where it appears. So I'm just going to write that. So I1 is equal to 0 minus, so which is negative v in minus v out divided by a divided by R1, which is also equal to v in minus v out divided by a minus v out and all over R2. So we're going to solve for this. Is kind of complicated, a lot of algebra, but we just go one thing at a time. So one thing we can do is this cross multiply. So if we do cross multiply, we get R2 and there's a minus, and then it's v in minus v out divided a, which is equal to R1s. So now we're multiplying here. V in minus v out divided by a minus v out. Okay. Now we need to distribute these terms. So the left side becomes negative R2 v in plus R2 v out divided by a, and then the right side becomes R1 v in minus R1 v out divided by a minus R1 v out. Now we will consolidate all the v in terms go to the right side, and then all the v out terms go to the left side. So this additions to here. So then you get the R1 v out plus this stays here. So R2 v out divided by a. This adds here plus R1 v out divided by a is equal to this goes to the right side, and this stays here. R1 v in, that stays here, but then gets the R2 v in from the right side. Now we can, I'm going to flip these two spots. Then we can distribute out a v out on the left side. So v out is here, and then we have R1 plus R1 divided by a plus R2 divided by a. Then on the right side we can distribute out the v in. Okay. And now we need to solve for the gain. So the gain is defined as v out divided by v in. So that is just like R1 plus R2 divided by R1 plus R1 over a plus R2 divided by a. And we can be done here but the textbook does some manipulations to this this gain equation in order to demonstrate a couple of important ideas. So we're going to do the same. First thing is, let's divide both the numerator and the denominator divided by r1. So then it becomes r1 plus r2 divided by r1 divided by okay, just do this whole thing, which is equal to okay, so the first term on the denominator is r1 divided by r1 is 1. The second term, the r1 cancels, and then the third term is, we're still stuck with the r1. Okay, now on the numerator, it becomes r1 divided by r1 plus r2 divided by r1, and then okay, let me just copy this denominator. So then it becomes 1 plus r2 divided by r1 divided by 1 plus, and then factor out the 1 divided by a. So then it becomes 1 plus r2 over r1. This is the gain equation that the textbook writes it as. So this is the non-inverting configuration. So non-inverting configuration with the finite a. Okay, for one moment, let us recall the inverting. The finite open loop gain, but it was on the inverting configuration. So recall the inverting configuration equation. That was so that was this one. There is some similarities across the two, but there's also some difference. The first similarity is they both have identical denominators. What's another commonality? So these are the list of commonalities across these two equations. What is another commonality? And as the op-amp becomes more ideal, meaning as a goes to infinity, we approach the following. In the case of the inverting configuration equation, as this goes to infinity, then this whole term goes to 0, then it's just divided by 1. So as the op-amp becomes more ideal, the numerator the gain closed loop gain becomes the numerator. Now let's discuss what happens on the non-inverting configuration as the op-amp becomes more ideal. So as the op-amp becomes more ideal, this term goes to infinity, then causing this whole term goes to 0. So then it's just divided by 1. So then like the circuit for the equation for the inverting configuration, as the op-amp becomes more ideal, the closed loop gain equals the numerator. So as op-amp becomes more ideal, so the meaning of that is as open loop gain goes to infinity, then the closed loop gain equation takes on the numerator. So drawing a parallel to the non-inverting configuration, so now we're discussing this for the inverting, it's drawing a parallel taken from the inverting configuration and applying it to the non-inverting configuration. It is important that we design open loop gain to be much bigger than open loop gain should be much bigger than the numerator. Why is it like this? It is due to, the reason is because it is due to the following term. So due to this term, it is very crucial. It is very crucial that we design A to be much bigger than this numerator value. And also another important another parallel that we have repeating from the inverting configuration. It is the same thing as before when we said there's like a percentage gain error between the ideal and the finite. So between ideal op-amp and the finite op-amp. Will not provide so I'm not going to go through how we can generate this equation, because we already did that for the inverting configuration, so I'm not going to repeat it here. But what I will just provide just the equation. So percent error is equal to negative 1 plus R2 divided by R1 divided by A, which as a finite number, plus 1 plus R2 over R1. And the conversion factor is going from decimal to percentage. Okay. And also, for the sake of sanity check, if the op-amp was ideal, so this was infinity, then this whole value goes to multiply by 0. So then percent error would be 0 if it was an ideal op-amp. Let's just go through some quick example. Say the open loop gain is 1000. And the circuit we designed was matching the resistance values in such a way we designed it to be the closed loop gain, the ideal would be equal to 10. What is the percentage error? We can, I'm not going to go through the derivations because that will take some time, but we can just say the real, it is around the 1% error, roughly around that. That's a value that within the general range that we can expect. The point is that even though this open loop gain may not be infinity, but the point is if you change this significant, it does not significantly change the overall gain. It does not have a finite open loop gain, does not have a huge impact on the degradation to the closed loop gain. Now, one last thing to talk about is let's do a discussion on input and output resistances. So this is just repeat from the inverting configuration, so there's no need to discuss it anything, but just as a reminder, we prefer R in is infinities, and we ideally would make R out 0. And just as a review from before, so why do we care about this? It's because we want the R in for the op amp to be infinity, so that this resistance, we want that to be infinity ideally, so that there's no current goes into the op amp. And likewise, we want the output resistance to be as close as 0, so it behaves as closest to the ideal as possible. So this is the inverting configuration, and for the most part everything stays the same. It's just that the gain equation is a little bit different from the inverting configuration. So, but all else, the inverting configuration, the non-inverting configuration, the gain equation, is the principle that I just want to point out, that as the op amp becomes more and more ideal, as A goes to infinity, then in either case closed loop gain takes the numerator value.